What's up, guys? Welcome back to Yoda Monk, and today we are going to take another session over system design, and we'll be discussing about distributed messaging queue. Now, here's the thing: when a service A calls service B directly, and service B slows down, service A waits. Service A's thread pool fills up. Service A starts timing out, and every service that depends on A also slows down. One slow service, and the system-wide cascade. You've probably seen this pattern. It's the default failure mode of any synchronous microservices architecture. The fix is straightforward. Stop calling service B directly, drop a message in the queue, and move on. Now, service B processes when it's ready, and if it's slow, the queue buffers. Now, if it's down, the message waits. Your service never blocks. Now, that's a messaging queue. And it's how companies like LinkedIn processes 7 trillion messages per day. That's the same fundamental idea. Okay, so let's go to the functional requirement. Think of it like a postal service for software. The sender, the producer, drops a letter in the mailbox. The postal system, the broker, holds it, routes it, and handles the retries. The recipient, the consumer, picks it up at their own pace. If the recipient is on vacation, the letters queue up. When they return, they process in order. Nobody waits for anybody. That's the model. Now, here are some of the things. There will be a service that will be producing messages that will publish to the named topic. Then there will be consume messages, that is to read from topics, track positions with offsets. Then we have the consumer groups, that is multiple consumers share work on one topic. Then ordering, per partition, ordering guaranteed. Then we have the message retention. We keep the messages for n days, reread the old messages. And then we have at least once delivery, that is no message is dropped. Then we have a dead letter queue. Park messages that fail processing repeatedly. Now, here's an interview trap. The interviewers ask, why not just use a database as a queue? The answer should be sequential writes, zero copy reads, and horizontal partitioning. A database can't match this throughput. There is a distinction worth internalizing. A messaging queue is not a database. It's an append-only log optimized for sequential input-output. That single distinction drives every design decision that follows. Let's go to the non-functional requirement now. We will work over this. So we have the throughput, that is 1 million plus messages per second per topic. Then we have latency should be lesser than 10 milliseconds end to end from producer to the consumer. Then the durability, that is zero message loss. Replicate to 3 brokers at least minimum. Then we have the ordering, guaranteed within a partition, not globally. Then we have the fault tolerance, survive the broker failures automatically. Now, the global ordering versus partition ordering. This is where most candidates slip. Global ordering requires one partition. One partition is equal to one CPU. That is not scalable. Now, that ordering row is worth pausing on. If you need global ordering, every message in sequence, you must use a single partition. A single partition means a single CPU thread writing to it. That's your throughput ceiling and it's low. In practice, you accept per partition ordering. All messages with the same key go to the same partition and arrive in order. Different keys might interleave. For most applications, that's enough. Okay, now we will enter the high-level design. There are 4 main roles in the system. First is the producer. The producer serializes a message, then picks a partition by hashing the message key or round robin and sends that to that partition's leader broker. Then we have a broker. Broker is the server that holds the data. Each broker owns some partition, appends messages to that partition's commit log, and replicates to the follower brokers. Then we have the consumer, which pulls the message from the broker. It tracks its position with an offset and commits that offset when done processing it. It can reread any historical offset. This replay capability is one of the things that makes message queues dramatically most useful than traditional job queues. Then we have the coordination service. Zookeeper or KRAF manages broker registration, leader election, and consumer group assignments, the brain of the cluster. Now, the partitioning model is the key design insight over here. One topic, 6 partition, 2 independent consumer group. If consumer group A has 3 consumers, each handle 2 partitions and share the work. Consumer B, if it has 2 consumers, that is completely independent of group A, it gets its own copy of messages. This means that the same stream of events can feed your analytic pipelines and your notification service and your audit log, all independently, all of their own pace. Okay, after going to the high-level design, let me bring back to you to the API and the data model level design. Let's go to the message format first. In the message format, the first keyword is offset that will tell the position in the partition log. Then we have the time set, that is the producer timestamp in milliseconds. Then we have the key, that is the partition routing key. Then we have the value. Value will be the actual payload value that is being passed through. Then we have the headers. It is a map which has a metadata like source, version, trace ID. Then we have the CRC. It is kind of a checksum that is used for integrity matching. Then we will have some APIs. One will be the producer API. It will be API v1 topics order event produce. That will have a body and the actual message in it. And its response will be like the offset number and in which partition it is stored into. Then we have the consume API. Consume API is used to consume the messages. It will be a get type API with v1, that is a version number, topic, order events, and consume. We will specify the group like the payment group, then the partition, which partition we want to consume from, and the offset and the max limit. The response will be the messages according to the offset we have passed. Then we have a post API that is used for committing. That tells that a particular consumer has already consumed this message. That is a commit message. Okay. The next is the topic configuration. It is another post API. We define how the topic and the replication factor and the retention looks like. These are the properties which will be put for the basic level configuration. Now, 3 producer acknowledgement modes are there and the choice matters. If ACK is equal to 0, it is fire and forget, fastest, and no durability guarantee. If ACKS is equal to 1, this means that the leader confirms it is fast, but leader failure means message is lost. If ACK is equal to all, this means that all ISR replicas confirm it is the slowest, but zero data loss is there. The production system uses ACKS is equal to all every time. Now we will deep dive into some of the components. The single most important insight in this entire system is something most engineers don't think about until they've seen a Kafka cluster handle the traffic they didn't expect it could. So first one is the commit log. In this, each partition is stored as a sequence of segment files. The segment 1 holds offset 0 to 999. Then segment 2 holds offset from 1000 to 1999. The active segment is currently being written. So 2 index files accompany each segment. An offset index that maps offset to byte position and a timestamp index that maps timestamp to the offset. When a consumer wants offset 1042, the broker binary searches the index for the byte position, then reads from the disk. It does not do a full scan. When a message is written, it's appended to the active segment. That is append only, no random writes. Now here is a secret. Every write is a sequential append. Magnetic disk with sequential access gets around 600 MB per second. With random access, the same disk gets around 100 MB per second. Now Kafka squeezes 6x more throughput from the same hardware just by virtue of this architectural choice. Then next component is the replication. ISR stands for in-sync replicas. The set of replicas that are fully caught up to the leader. When a message arrives at the leader, it appends to the log and then sends to all the ISR follower and waits for all the ACKs. ACKs is like acknowledgements. Only after the quorum acknowledgement does it acknowledge the producer. If a follower falls behind, it's removed from the ISR. If the leader fails, the coordination service detects the missing heartbeat. That is around 30 seconds by default. It can be reduced to 10. Then a re-election happens for the new leader from the ISR. And then the producers and consumers redirect automatically. Now here's why ISR membership matters. Only ISR members can become the leaders. If you allow a non-ISR replica to take over, you could elect a broker that's missing the last 10,000 messages. So messages you thought were committed are gone. Okay, the next part is the producer and the consumer flow. Now producer hashes the key, determines the partition 3, connects to the partition 3's leader broker, and then sends. Then the broker appends to the segment file, that is a sequential write, and it replicates to the followers in parallel and then waits for ISR acknowledgement and then returns the offset to the producer. Then the consumer polls for the messages at offset 1042 on partition 3. Broker reads from the segment file using a zero copy send file system call. The OS transfers data directly from the disk buffer to the network buffer. It never copies to the user space. The consumer processes commits offset to 1142. So the zero copy roughly doubles the read throughput. It's one of those implementation details that looks trivial but have massive real-world impact at scale. Now, after going into the deep dive, we will go into another section which is very important and asked in almost all system design interviews, that is the observability. So here are some of the observability things. Now, consumer lag is everything in the system. So zero lag means consumer are keeping up and healthy. Then growing lag means they are falling behind. Add consumers or optimize the processing. Now, the lag of 50 million means you have messages queued up for hours and downstream services are working with the stale data. Now, in this case, alert a lag above 100,000, page at lag level above 1 million. Now, those are the thresholds that actually matter in the system. Okay. So, here are some of the failure points which are very important for this. First failure could be a broker failure, that is the leader gone. Now, when the partition leader crashes, coordination service detects missing heartbeat. This is 30 seconds by default, but during those 30 seconds, producers get connection errors and consumers get no messages. The fix is reducing the heartbeat timeout to 10 seconds. In this case, you'll get slightly more false positive on transient network blips, but a 10-second gap is far more acceptable than a 30-second one. New leader gets elected from ISR, producers and consumers, then reconnect automatically. Another failure that can happen is what if the consumer rebalance storm is happening? That is 10 consumers in a group, one crashes and rebalancing starts. In this case, all consumers pause. New partition assignments are computed. All consumers in that case then resume. This takes around 5 to 30 seconds during which nothing gets processed. If 20 consumers crash and rejoin rapidly, in that case, you get continuous rebalancing. The system processes nothing while it keeps on reshuffling. Now, the fix is static membership. Assign each consumer a fixed member ID. Rebalancing only triggers if a member doesn't rejoin within a longer timeout, that is around 5 minutes instead of 30 seconds. Now, this tolerates the rolling restarts and transient crashes without triggering a full rebalance every time. Another failure that could happen is the message poison or the poison message. What if one message crashes the consumer every single time? So the consumer crashes again and it goes in infinite loop and infinite loop. Now, consumer is stuck at this offset. The lag grows and all downstream processing halted for just one bad record. Now, the fix is a dead letter queue with a retry count. After 3 failed attempts, move the message to the DLQ topic, log the failure and continue processing. Humans inspect the DLQ on the schedule. This never blocks the entire pipeline for one bad message. Okay, so here are some of the improvements which we can do in our message queue system or distributed messaging queue. The first one is we can have exactly once delivery. At least once is the default. A message is redelivered if a consumer crashes before committing the offset. So applications need to be idempotent. For financial data, idempotency isn't enough. You need exactly once. Idempotent producer assigns each message a sequence number. The broker deduplicates by producer ID plus the sequence. Transactional consumers read the message, update the application state, and commit the offset all in one atomic transaction. The cost is 10 to 20% throughput reduction, and it's worth for money movement. Then we have the log compaction. Now, the standard detention deletes messages older than 7 days. All history is gone. Now, the log compaction keeps only the latest message per key and deletes the older versions. For example, if we have a order status updates where the key is the order ID, only the latest status matters in this case. So the compaction removes the intermediate states but retains the full current snapshot indefinitely. This is used in database change events where the user preferences updated inventory snapshots. Another improvement we can do is the tiered storage. Now, local disk gets expensive at petabyte scale. So after 7 days, move the segments to S3. Keep only the recent messages on the local disk. Consumers can still read historical messages. The broker streams from S3 transparently. This helps in cost reduction. We can reduce roughly 90% of the messages older than 7 days with no change to the producer and the consumer API. Okay, so the messaging queue is a shock absorber. It decouples producer speed from consumer speed and lets slow services recover without taking fast service down with them. Remember the cascade we discussed in the start of the conversation? One slow service brings down everything downstream. Queue is in the middle and that cascade never happens. Now, 3 things to take away from here. Append-only commit log gives you a sequential I/O and 600 MB per second throughput on commodity hardware. Then the consumer offset is the consumer's responsibility. Pull-based, consumer controls the pace, never blocked by the other consumers. Then we have the ISR replication. This means only in-sync replicas become the leader. So no messages are lost on broker failure. Now, same architecture that runs 7 trillion messages a day on LinkedIn. It's very simple idea, but at a massive scale. Then see you in the next tutorial.